All right. So looking at the first question, we see that it is a exothermic diagram. And we see that because the products are lower than the reactants. If we look at this, we see that the reactants energy is right here and the products is down here. So that means some energy was released, making it exothermic. And the question is asking to draw one that is endothermic. So that means the products will be above the reactants, but occurs at the same rate. Does anyone know what affects the rate of a reaction? Yes.
Is it heat?
Heat, not
Temperature
necessarily.
temperature does affect the rate, but in this case, um, we'd be talking about something different on the diagram, which is the EA, activation energy.
Yeah, so the EA is known as the rate determining step. The EA is the activation energy. So we see that this right here, I'm drawing in blue, is the EA. So when you're trying to draw one that has the same rate, you want it to have the same EA. So we're going to start here. And we'll draw about the same, and then we're going to end. So this would fit the criteria that we need. Our products are higher than our reactants, and the EA is the same. So just like a key concept to know is that the EA is the rate determining step. That makes sense? You understand that? Next, we're looking at this, and it's asking us to determine if the stereocenters are R or S, and also to indicate the priority labels. So looking at this stereocenter right here with the blue, we see that oxygen will be our 1, this will be our 2, and this will be our 3. And then we can draw in that hydrogen. So we see that the lowest priority group is on that dash, so we can just assign RS as is. So it goes this way, making it S. Make sense?
I didn't know which way to went. That's why I put in like instead of
Are you talking about the hydrogen?
Yeah.
It wouldn't matter if it went up or down. Because say I drew it up here, you would still count it like 1, 2, 3. So it'd still be the same. Moving on. Looking at this nitrogen, use a different color. This group with the nitrogen. So nitrogen will be 1. Then we'll have this side be 2, and this will be our 3. And we can draw in that hydrogen, and that will be our 4. So because the hydrogen is on the wedge, we know that we're going to assign RS as is and then flip it. So as is, it goes this way, making it S, and then we flip it to be R. That's just one of the rules that we learned. So when the lowest priority group is on the wedge, you just assign RS as is, and then you flip it. So that is R. Next, we're going to be looking at the mechanistic arrows. So we're going to be drawing those, and we're going to label them as our 4 arrow pushing patterns. So our 4 patterns are nucleophilic attack, loss of leaving group, rearrangement, and proton transfer. Yes. So looking at this first step, we see that we get a new bond right here to this carbon. Something is happening there. So we see that this group is now here. So we can draw that arrow to there, and we see that this double bond is going on to that oxygen to make it negative. When you're drawing arrows, you want to make sure that you're always starting your arrows from a source of electrons. So on this oxygen, There are lone pairs, and that's what we're using. Does anyone know the name of this step?
The first one.
Nucleophilic attack. That's right. So that is a nucleophilic attack. Next, we're looking at these two. And the difference that really stands out is that this hydrogen is no longer present in that product. So that means something needs to take that hydrogen. So we can draw this picking up the hydrogen, and the bond will go to the oxygen. Right? Does anyone know the name of that one? Yes. So we see that in the product, there is no hydrogen. And in the reactant, it has this hydrogen. So something needs to take that hydrogen away. We know that there is electrons right here that can pick up that hydrogen. You can take it. And then the bond is broken and goes to the oxygen. So do we know what that's called? Kinda. Yeah, proton transfer. It's a specific type of leaving group. All right. And then for the next step, we see we're comparing, always compare the reactants and products, see what's different. So we see that this one has a chlorine and the chlorine is gone here. So what you would do is you kick that chlorine off, and then we see there's a double bond right here on this oxygen. You can reform that double bond. Does anyone know what that is called? Specifically, the leaving of this chlorine. There's a loss of leaving group. Does that make sense? It's about as hard as it will be on the quiz. Specifically, when there are multiple steps like this, you have to be able to determine what is like the mechanism and what it's called. All right, and then we're going to draw the chair flip. So the first thing you want to do is draw it in the opposite direction. And then what is up axial becomes sideways equatorial. So we see that this OH group is going to become equatorial. And then you also shift it one carbon to the right. So that puts it there. We see the chlorine is up. So then it's going to become equatorial. And then the methyl group right here is equatorial. So it's going to become up.
Straight down.
I shouldn't have said up. I should have said axial because it's actually pointing down. Make sense? Chair flips, pretty simple. What's equatorial becomes axial, and what's axial becomes equatorial, and you just shift it over right one carbon. Next, yep.
Just shift it over carbon.
And if it's axial, it becomes equatorial, and if it's equatorial, it becomes axial.
But notice that the direction of the substituents don't change. If it was up, it's still going to be up. If it's down, it's still going to be down.
Yep. Next, we're going to label these as enantiomers, diastereomers, constitutional isomers, identical or different. And remember, enantiomers are all chiral centers are flipped. Diastereomers are one, but not all. Well, I could say some, but not all. Constitutional isomers, they have the same formula, but different attachments. And then identical are the same and different is different. So how I would start out this is I would draw out that chair structure to match the other one. So we see that we have a bromine that is going down. And then we have this chlorine going up right next to it. Then we skip 1, 2 carbons. We're going to skip these two. And then over here, we have a OH going up. and a methyl going down.
Dash.
Yes. Just like that. Now, can anyone tell me what relationship these two have with each other?
Who thinks it's an enantiomer? Who thinks it's diastereomers? Okay, one person. Who thinks it's a constitutional isomer? All right. Who thinks it's identical? Who thinks it's different? So majority of you guys think it's different then.
Can someone say why they think it's different? Yeah. Kinda. So when you are trying to determine this, make sure you're counting out all the molecules. So we look at this. This has one oxygen. It has one bromine, one chlorine, and then we count out the carbons. We have 1, 2, 3, 4, 5, 6, 7, 8. I'm gonna redraw this methyl so it's a little more clear. So we have 8 carbons, and then we're gonna count out the hydrogens. So we have 1, we have 3 here, 2 there. So that is 6. And then we have 2 more, 8, 10, 11, 12, and 14. So we have 14 hydrogens. Right? And then on the next one, we do the same thing. So it's both going to have one oxygen, one chlorine, one bromine. And they both have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So next thing we do is we count out the hydrogens. There's 3 hydrogens here. Then we have 3 here. That's 6. Then we have 8 from there. We have 10 from there. 11, 12, and 14 hydrogens. So does that change some of your answers? We see that they have all the same molecules. Remember, different is that they don't have the same amount of molecules. So having the same exact molecules, but they're connected differently, means that they are constitutional isomers. And we can see that they're not connected differently because here there's 2 carbons between the bromine and the methoxy, and also there's a methoxy instead of an OH, whereas here there's only 1 carbon and then it's an OH group. So we can see that they're connected differently. Next, we're going to look at these chair structures. First thing I would do is probably draw them out. So we have this front carbon with an OH coming towards us. We have the H behind, and we have a methyl going up. And then on the back carbon, we have a methyl down. We have a OH coming towards us. And we have an H in the back. That's this first structure here. And then for the second one, we have an OH going back, a methyl coming towards us, and an H on top. And then on the back carbon, we have OH on the bottom, an H coming towards us, and the methyl going back. So what you want to do for this is assign R or S for each of the stereocenters. So for this first one, we have OH as 1, then this will be our 2, this is our 3, and this is our 4. So that is S. And for this back one, this is our 1, this is our 2, our 3, and our 4. So we go this way, and that is also S. Looking at the other one, we have this as our 1, this is 2, this is 3, and this is 4. We see that the hydrogen is in the plane, so we need to do that flip that we learned to get it on the wedge. So we'll flip it these two, and we'll flip these two. So that gives us something like 1, 3, 2, 4. And then assigning it, it would be S. And then for this back one, you have 1, use a different color. 1, 2, 3, 4. We see that the lowest priority group is on the wedge, so we'll just assign it as is. It goes this way, making it R, and then you flip it because the lowest group is on that wedge. So that's also S. So can anyone tell me what kind of relationship these two have with each other? Yes, they are identical. Okay. And then last, we're going to draw the arrow pushing mechanism and the major product for this reaction. Yes.
They just because they both have the S carbonates.
And they also have all the same molecules attached to the same things. So first thing you want to do with this is you're going to start your arrow at a source of electrons. And a source of electrons in this case would be that double bond. So you can draw it to pick up that H. This bond will break and go on that bromine. And what that looks like is and we got that H that went there. And we know that when it's just HBr, the H is going to go on the less substituted side, and the Br will likely go on the more substituted side. There's an important thing to note when you're at this carbocation is that rearrangement is possible. This is something you should always look for when there is a carbocation. So we can do this rearrangement here, and we get this. And then from there, we still have this bromine with a negative charge. We can do a nucleophilic attack, and that gives us